Alright, so in this video lesson we are going to learn how to perform a chi-square test for goodness of fit. And it is highly recommended that this video lesson is viewed after you have viewed my other video lesson on how to use chi-square test for independence. So now allow me to bring up a problem here. And I will be using this problem to explain about the details of the chi-square test for goodness of fit, as well as what it means by doing goodness of fit. And later on, in the later half of this video lesson, I am going to also push this particular problem forward to become an actual example of ours. Alright, so let's spend some time reading the wording description of this problem that was brought up here with us. So it is claimed that 40% of the student population who took or enrolled in a certain math course is in business major. Similarly, 30% is in nursing major and 20% is in an engineering major. So I'm saying an engineering major here simply because there are a lot of engineering majors out there. And so for a student who is taking this math course, for whatever that math course is, 20% chance that student can be in an engineering major of some kind. And the rest, 10%, is undecided about their major. But now a sample is selected and show the counts as described in the table. And so the sample here that the problem is describing is the sample that, of course, being selected throughout all students who took or enrolled in that whatever math course is. And so let me now show the table. This is the table that we are looking at. So now here's how I organize the data that we have read in the wording description of our problem earlier into a table like this. So these are the different majors that that's being mentioned in the problem. So there is business major, there is a nursing major, there is engineering major, and there is someone who is undecided. And so this is our sample right here. I sample 50 students or sample. And inside of this 50 students, the count show that and of course, these students are all enrolled in that whatever math course was. And so in this sample of the 50 students in the math course currently talked about, then the count shows 21 of those students in this sample are in business major. 8 of those students in this sample are in nursing major. And of course, let's assume again that whoever is in one major is not double major with the other major. So no one in this sample is a double major. Basically, that's what I'm trying to express right there. And so if you're in a nursing major, you're in a nursing major. And then for engineering major, in this sample, we found a count of being 6. And then 15 of those are undecided, which is a very common thing for a college student. And of course, this wording here, even though without a specific description, but is intended for, it's a math course at a college level. And so now back to the wording description here, let's find out what it means about all this description before the description of the sample. So it is claimed that 40% of the students of the student population who took or enrolled in a certain math course is in business major. And similarly, 30% is in nursing major, 20%, of course, all of these percentage came out from the student population as set here. So 20% is in an engineering major and 10% is undecided. So according to this description, what it says now is that, you see this empty column right here that I have prepared on my table, it says population. And so this is how I can put the description from the problem into the table as following. So business major. So now all of these different majors are different categories for the student population who are taking that math course. And so for business major, in the entire population of students who take that math course, then according to the description, 40% of the student population is in business major for that math course, of course. And so that means now, back in my table here, in our table here, now I can write that as a 40%. But it is actually a requirement that we put these percentages now as a decimal. So 0.4 is the population proportion of business major in that population. And so this 40% here is the proportion of business major in that population. And so the idea now is that we don't really know how big the population of students in that who take that math course, but this is a claim, as it's said right here. It is a claim that. So that is now how we are trying to verify whether the claim here is correct. So it's claimed that, so it's only right now a claim, it's claimed that the proportion of business major in this population of students is 40% or 0.4. Then continuing further into the description of our problem, let's one more time have a look. Similarly, 30% is in nursing major, and now I have all these numbers to be filled into the board, to the table. So 30% is in nursing major, 20% is in an engineering major, and 10% is undecided. So that now means we have the population proportions being distributed as following. So we already had 0.4 or 40% is the proportion for the business major. So now nursing major is going to be 0.3 as for 30%. Engineering major is 0.2 as for 20%, and 0.1 or 10% for undecided. And so now here's what to understand further about this problem, about this claim right here. It is claimed that 40% is in business major, 30% is in nursing, 20% is in an engineering major, and 10% is undecided. So in the way how it is, really, it is one claim that claims the truthfulness of all of these claimed proportions. So in the role of this table, this column here under the label population lists all of the population proportions. So here we got 4 categories. In this entire population, think about the whole population of students who are taking that math course for whatever that math course is, then the entire population there is split it into 4 categories. There's business major, there's nursing, there's engineering, and there's undecided. And so the claim is stating that all of these are the proportions corresponding to these different categories here. So in the way how we should be understanding about it, one claim claims for all 4 population proportions at once. And so now to have a preview ahead of time, then the idea now is that in this sample, we want to find out if this sample agrees with all the proportion, with all the population proportions being claimed, being stated in our claim as described in this column right here. So that's why this sample, the counts that came out from the sample are regarded as the observed counts. So these are the observed counts. So we actually found that 21 of the students in this sample are in business major, and 8 of the students in this sample are in nursing major, and 6 of the students in this sample are in engineering major, and then the rest is undecided. And so after having a thorough understanding of what the 2 columns here are, as well as what the difference is between them in our table, which is a common practice anytime we're performing a chi-square test for goodness of fit, there will always be a claim that claims the value of multiple population proportions, which will then be recorded in a designated column. Each of those proportions is the proportion of one separate category in a population. And then there is another column where we're stating our counts found from a sample from that population. And so in that way, back to what I was saying in the middle, once we have had a good understanding of the table and as well as the data being given to us, now the question is brought to us as following. At significance level, so when anyone has arrived at this video lesson, then the person should be well familiar with the concept of testing a hypothesis. And also, I highly recommend watching this video lesson after you have seen or have watched my other video lessons about testing a hypothesis. So this symbol here, assuming that you have watched my video lessons on testing a hypothesis, then alpha is a symbol for significance level. So in a way how it reads now, at significance level given at 0.001 is a sample described in our table just now, showing strong evidence that not all population proportions claimed are correct. So what it says now is that in the end we must understand further that these are only values that are claimed. So somebody claimed this, or some department of the school claimed that to us. Now we want to look at our sample and verify whether this claim is true. And so as a little bit of a deeper understanding here, then in what I said earlier, this is one claim but claims 4 different values in one statement. And so once the claim is made, the impact of the claim is that if it was true, then it would be true for each of the 4 values here, meaning the values stated in this column would be all correct. So many people might believe in a claim or accepted the claim as true, but now as we're looking at the sample, let's see if this sample would show strong evidence to prove that not all population proportions are correct. In another way of saying, not all population proportions claimed are correct means some of the population proportions claimed here must be incorrect. And that's the whole intention of this. And so 4 population proportions are claimed here, but we now want to prove that some of these proportions must be incorrect. And so in the end, after all of the explanations, the question itself appears to be a testing hypothesis problem because it has that part here asking, is the sample showing strong evidence? So we want to prove that not all population proportions claimed in the table are correct. And this highlighted part of our question is ringing a bell for us that this problem is a testing hypothesis problem. And so now, as soon as we have recognized that the problem we're doing here is a testing hypothesis problem, then we need to, as our first responsibility, identify the 2 hypotheses, H0 and H1. And so now H1, the alternative hypothesis, we can just simply copy and paste the statements from our wording of the problem. Not all population proportions are correct. And allow me to skip the word claimed here. Of course, these population proportions are claimed. So that's what H1 is saying, the alternative hypothesis is saying. Not all population proportions are correct. So some of those among the population proportions being listed in that column you have seen in the table must be incorrect. But so now if the alternative hypothesis H1 is stating this way, not all population proportions are correct, then H sub 0 must be saying all population proportions are correct. And so let me again remind, under the assumption that you have arrived at this video lesson of mine after you have watched or seen my other video lessons on testing a hypothesis, and as well as performing a chi-square test for independence, then in the way it is, the null hypothesis and the alternative hypothesis are always the counter arguments of each other. They are always arguing against each other. So another way of saying h1 and h sub 0 are always saying the opposites. So if h1 can be recognized as easy as copying and pasting the statement from the question, not all population proportions are correct, then we can just simply now construct h sub 0 as saying the opposite way by saying that all population proportions are correct. So let's now get started into performing the test to see if all of these are correct or some of them must be incorrect. So let's say if we start out with accepting that all of these population proportions are correct. Think about it. If all of these population proportions are correct, say for example, if it was correct that among the population of students who took that specific math course, 40% of them is in business major as stated, then in this sample 50, I am expecting the following. So as a scratch work, if it was true that 40% of the students' population is in the business major as listed in the table you have seen previously, then in the sample of 50 students, this is our sample size, the total at the bottom of all of our observed counts here. And so now multiplying the sample size with this population proportion that is currently accepted to be the truth, then we are going to come up with a count. Calculation shows that 50 times 0.4 equals 20. This is a business category. And seeing this as one of the categories, we can call this category 1. So what I did there, I multiplied the sample size with the claimed population proportion for this category 1 or the business major. We came to this value right here. So 20 now is being referred as the expected count. So here's the way how the logic happens. If this population proportion claimed here was true, then in this sample, I expect that. So now I'm going to go ahead and write in, I expect that 20 of the students in this sample should be in the business major. So that's how I called it the expected count. So I expect 20 of them in this sample to be in business major if this population proportion was true. So now before we move on to the next step, anyone viewing this video can start noticing that the expected count already appears to be slightly different with this observed count already, because in the actual sample we already found up to 21 students being in business major. So this is observed count and this is expected count. And so as a further clarification, so I treat business here among our categories as category 1. So this expected count here is referred as E1. So if any one of the viewers who is watching this video lesson has seen my earlier video lesson about performing a chi-square test for independence, then the major difference here is that each expected count here gets only one subscript instead of a pair of subscripts. And so I highly recommend getting for yourself into the habit of recording the expected count as a third column as being described in my current table right here. And so let's move on to the next category, namely the nursing major in this student population who are taking that whatever math course that is. So it is claimed that the population proportion of this major is 30%. So if H sub 0 was true, meaning this population proportion was also true, because again, I keep emphasizing that one statement, the null hypothesis statements, claim that all 4 of these are correct. And so if all 4 of these are correct, meaning this population proportion was also correct. And if that was so, if that population proportion here of nursing major was also correct to be 30%, then in this sample, I am expecting, back on my writing board, now we are currently at nursing major. We can namely refer to this as category 2 among all of our categories in this population. So I am going to do the same way. I am expecting that in 50 of my students in the sample, multiplying that with 0.3, I am expecting that 15 of the students in that sample should be in a nursing major. And so again, this number is now also referred as expected count. But this is the expected count for category 2, the nursing major. And so I now call that E2. And now I am going to record that into my table in the third column. So I expect that among 50 students in our sample here, 15 of them should be, and I'm using that term, should be in nursing major if this proportion was correct. But now, before I move on to the next step here, anyone viewing this video can start noticing that 15, the expected count here, is quite different from the count that already observed right in this sample. So in this sample, there actually was only 8 students who are in nursing major. But the expected count, the count was expected to be this high in 50 students. And now, after being done with the nursing major, let's move on to the next major, engineering major. If the claim in H sub 0 was correct, again stating that all population proportions claimed here are correct, then this population proportion itself, specifically for engineering major, must also be correct. And if that was so, if this population proportion was correct, being a 0.2, then in a sample of 50 students, I expect that for an engineering major, any engineering major, and we can refer to this as category 3. Again, back to what I was in the middle of saying, I expect that in 50 of these students, multiplying that with 0.2, my count must be a 10 as expected. I expect that among the 50 students in our sample here, if 0.2 was correct, then there should be 10 students among the sample here who are in an engineering major. And so again, this count is referred as the expected count for category 3. And symbolically, we can call that E3. And now we can fill that in to the table here. I expect 10 students in this total sample to be in an engineering major if that population proportion was correct. And again, I can already quickly see a difference. I'm not making a judge about how big or how small that difference is, or whether it's an acceptable difference, but it has already shown a difference between the expected count here that we recorded down and the observed count that was actually observed and recorded here with the in this table and inside of our sample here. All right, so now after getting the expected count for engineering major, let's move on to the undecided, the group of students who are undecided in their major among this sample. And so, again, the null hypothesis h sub 0 said that all of the population proportions here are true. So if that was so, then this population proportion for undecided major students was also true. So if this population proportion was true, then in my sample of 50 students, let's see what we can expect. For undecided major, and we can now refer to this as category 4. Then I am expecting that in my sample of 50 students, about 10% of those should be undecided about their major, and that's why I multiply 50 with 0.1, and so it gives me 5 right here, and this 5 is referred as another expected count, and this is expected count for specifically category 4, so I call that symbolically E4. And so let's now record that into the table. And so now, before we move on to the next step, and right after we have successfully found all of the expected counts here, then you can see that some expected counts stayed close with the actual observed count, and some other expected count stayed quite far, and even quite far. And so that is the reason why we need the next step here. But in the end, each of the expected counts here makes some difference with the observed count, and the difference could be large or small, like this case here, or large. Or there are even cases where the expected count might come to equal exactly with the observed count. In those cases, it's a zero difference. So there will always be some kind of difference between the expected count and observed count. And that's what we're looking at in the next step. And so now, as the step to perform our test, for our chi-square test for goodness of fit, then step 1 was just now done. What we did there was to find, or it was a step where we were finding all expected counts. Because again, if h sub 0 was true, claiming that all proportions stated in the table are correct, then it's gonna, any one of the population proportions will produce for us an expected count. So it was our first step here to find all expected counts. So in this problem we had 4 categories, and we ended up with 4 expected counts as described in the table. So now that was the step that was done. And now let's take a look at the table here as we're moving on to the next step. Now I am going to produce the 4th column right here, and as of right now it's empty. And I label the values I'm about to calculate here being the components. And these are, as a quick reminder, these are all the expected counts that we have calculated previously. And so now this is how I see it. Looking right at the first expected count, or E1 right here, I notice there is a difference between the expected count and the corresponding observed count. So this is observed count being 21, expected count is being 20. And so now I am going to perform the following calculation, specifically for business major, or again category 1. The calculation that I was in the middle of saying is as following, from where our observed count is. And similar to what you have learned from the video lesson about using a chi-square test for independence, I am again using capital letter O for observed count. So observed count in category 1, I'm now going to call that O1, and we don't need a subscript as a pair. So observed count in that entry, I'm going to subtract the expected count. Then I'm going to square the difference, and divided by the expected count for that particular category, namely category 1. And so the actual calculation here would be 21 for the observed count, subtracting 20 for the expected count, then square the difference and divide it by 20. So I call this value here a components value, and symbolically COMP with a subscript 1. And so here it's only a one single subscript value right here. So component COMP is short for components. So what I'm calculating here is referred to as the components value, or for short, just components. And since it happens in category 1, so symbolically I call that COMP subscript 1, components 1. Final calculation value came out to be 0.05. And for the rest of the lesson here, and with many other lessons about performing a chi-square test, anytime it comes to component value, I will round to 2 decimal places unless being specified otherwise. But again, I am leaving that responsibility for viewers and students to watch for your own routing requirements in any of the problems that you are doing. And so this is my components value for category 1. So now on my table, I am going to enter that component value into the first entry of our blank column just now created. So this column here is to record all component values of all different categories here. And so now let's move on to category 2, namely the nursing major. So according to the table, I noticed there is a difference between expected count, and it's quite far. 15 is the expected count, whereas observed count only showed 8 in our sample. And so now on my board, we're currently at category 2, which is the nursing major. And again, very similar work to be performed here. I am going to look at the observed count in that category. That's what O2 is for. Then subtract the expected count already calculated for category 2. That's what E2 is. The difference there is going to get squared and divided by the expected count. And this final value here, whichever it will come out, will be regarded as components value in category 2. And so the calculation will be set up as following. 8 is for the observed count minus 15 for the expected count. Square the difference and divide it by 15. Final calculation of mine into decimal shows that it's 3.27, even though the actual calculation was supposedly a lot longer than this. And so now this is my component value for category 2. So comp 2 is 3.27. So now on my table that I have prepared, the next entry down in the fourth column is now recorded as 3.27. So this is our components value for category 2, the nursing major. And now let's move on to the third category, category 3 right here, and for engineering major. I noticed that expected count was calculated as 10, meaning in this sample of 50 students, I expected that there should have been 10 students in this major if this count was correct. But now the observed count was saying something quite otherwise. And so in that way, let's calculate and find out what our components for this third category would be. So now we are at engineering. and that is referred as category number 3. Then again, from where our observed count, symbolically O3, I am going to subtract the expected count, symbolically E3. Square that difference there and divide that by E3. We refer to this as the component value, COMP3, components 3. And so the calculation setup will come out as following: 6 for observed count minus 10 for the expected count, square the difference and divide it by 10. Final calculation showed a 1.6 after all proper rounding. And so now on my table here, I will be entering 1.6 into the third entry, or the third category of our fourth column here, to list all of the components. And so now we're on our way heading out to the last category, being an undecided major in this sample. And so again, I expect that it should have been only 5 students being undecided with a major if this population proportion was true. But we found 15 of them actually in the sample to be undecided. And so let's look at how the calculation for component value will come out. And so now for the last category here, being an undecided major, as category 4, components here symbolically comp4, observed count in the fourth category, subtract expected count in the fourth category, then square the difference and divide it by E4. So the setup will come out 15 for observed count, subtract 5 for expected count, square the difference and divide it by 5. And so final calculation after rounding, to be consistent with the convention stated earlier, came out to be 20. And so now we can record that components 4, the component value, into entry number 4 in our fourth column to be 20 on the computer screen here. And so what we did just now was to find all component values corresponding to all 4 categories. And so at the end of that step there, that was our step 2. So anytime that we're performing a chi-square test for goodness of fit, second step, or the step right after finding all expected counts, was to be that step where we were calculating all components or component values. And that was the step we just now got done. And now once we have successfully calculated all component values, or for short, components, the next step after that is to calculate the chi-square. And so chi-square is calculated as the sum of all components. And so in this case right here, recall for ourselves our last result that we have found. We have now found all components of our 4 categories. So that means our chi-square is calculated as following. 0.5 is the components for first category. I'm going to add with 3.27 as the components for second category. I'm going to add again to the third component value being 1.6 here. And I'm going to add to the last component value being 20. Calculation of mine shows, and of course, in the way how each of the components here is rounded to 2 decimals, then the final answer as a chi-square value is needless to say in 2 decimal places, unless any time being otherwise specified. And so our final chi-square is at 24.92. And now in that fourth column at the bottom, I decide to put the total here. That's corresponding to this total row here. So this is the total of all component values. And as another name, this is our chi-square value. And so, formally speaking, after calculating all component values, then step 3, or the step right after calculating all component values, is the step that's calculating this chi-square value. And as a quick summary of what we did there earlier, chi-square is found by getting the sum of all components. And that's something to be highlighted. And now this information I'm about to write down is not formally a step, because that can be taken at any point. It can be done before getting into step 1 or before any of the steps here. The degrees of freedom of our problem is going to be 4 minus 1. So 4 came out from the number of categories we had in our problem. So in this problem, we organized our problem into a table. But in the end, this table here, or this problem has or describes about 4 categories, works with 4 categories. And so that's what this 4 is. So degrees of freedom for our problem here is 4, and then minus 1. And so that's why I'm saying it's not a formal step, because this step can be taken at any other step, and it's not necessarily dependent on any of these steps here. And so our degrees of freedom of the problem is 3. So generally speaking, degrees of freedom for chi-square test for goodness of fit can always be calculated by the number of categories. Minus 1. And that's another formula to highlight for the day. And again, remind yourself that this particular step is not dependent on any of the other steps. So formally speaking, I never regarded this as a step, because it's something we always need to calculate, but it can be done before starting into any of the steps here, or it can be done way at the end or in the middle, anywhere. And it's a truth that exists with any problem that we're performing a chi-square test for goodness of fit. All right, and so now after calculating our chi-square and knowing that our problem here has degrees of freedom 3, the next formal step is to calculate the p-value of our sample. Because again, what we have here is a sample, and so somebody else can find a different sample of 50 students, and who knows that in other sample of 50 students there, the observed counts might come out differently. That might come closer to agree with the population proportions distributed here. And so that's why in this case here, we want to calculate the p-value of this particular sample to decide whether or not we're having strong evidence to reject the acceptance of this H of 0 statement. So I am going to calculate p-value as following. I am going to fire up a probability calculation where among infinitely many chi-square values out there, we're going to find a chi-square greater than or equal 24.92. And so let's take a quick pause here and for me to mention and clarify a couple of details about the setting up of our p-value calculation here. So if anyone has viewed my video lesson about performing a chi-square test for independence, then this would be the same here. The inequality in our probability calculation is always a right tail. And always a right tail, I mean all the inequality symbol itself is always pointing to the right hand side. And just like that, this is our chi-square value. This is our chi-square that we have calculated from step 3. And so now to find the actual value of this probability setup right here, or namely it's the p-value, it's our final p-value. I'm going to leave that for our TI-83 or 84 calculator to handle. So on the home screen, I am going to hit second variables, which will bring up all of the distribution functions in statistics. I'm going to scroll down and look for the option that says chi-square CDF. I'm going to hit enter. So the version of the TI-84 calculator I'm using here is relatively recent. So after calling the chi-square CDF command, you will see a menu like this being printed right on your home screen. But be aware that on the TI-83 calculators and some of the earlier TI-84 calculators, and earlier I mean the earlier versions of the TI-84 operating systems, then after calling the chi-square CDF command, instead of seeing the menu like what you have seen earlier, you will see the actual command being printed right on your home screen. And I will shortly get back to this, showing you how to complete your command. But so now on the actual calculator that I'm planning to use, the lower end would be 24.92. And this is because according to the inequality setup written here, then this 24.29, which was our calculated chi-square value, was the low end. And in the way how it is here, we have an indefinite upper end. And so in that way, I'm leaving lower end to be 24.92. But when it comes down to the upper end, I am going to enter 1E99. And again, if anyone is unsure about how to do that, the EE is found right above the comma key right here. So 1E99. Our problem is working with degrees of freedom 3. So I'm going to change this to 3. And now I'm going to hit enter a few times and getting our command ready for work. And so if you are having a calculator that instead of a menu like what you have seen earlier shows the direct commands right on your home screen, then you must type in the low end, the high end, and the degrees of freedom manually. So low end is always first, assuming that you are using a TI calculator. So 24.92. And I'm going to put a comma after that. The upper end is 1E99 with another comma and degrees of freedom 3. Then we complete the command with a closing parentheses. And so now let's get to our final value here. So hitting enter is going to give me a value as following: 1.604675, and a lot longer with an E minus 5. So this is the value that came right out from the calculator. 1.604675 and a lot longer, and with an E minus 5. This answer on the calculator means our value was 1.604675 and a lot longer times 10 to the negative 5. So this is the way how the calculator is printing it, but it means scientific notation, base 10 to the negative 5. And so our actual final answer there is 0.0004 zeros before the first non-digit, and then 604, 675, and a lot longer. And unless being specified otherwise, final p-values for all of my video lessons will be rounded to 4 decimal places. And I leave that responsibility for viewers and students of mine to watch for any of your rounding requirements when it comes to final p-values. So here it's rounded to 0.0000. And so now that we have learned that our final p-value was 0.0000, calculated and indicated here as the standard step for deciding whether we're having strong evidence or not, we need to compare this final p-value as the next step with a significance level given in a problem. And what we want to find out is whether our p-value will fall below the significance level or above the significance level. That's what we want to find out. And so now back to the wording of our question, then right at the beginning, and I have highlighted this earlier, and now I'm going to highlight that again. At significance level 0.001. So that means we already had a given significance level for this problem. So that means our final calculated p-value will be compared directly with 0.001. And so now direct comparison shows that our final p-value is well below the significance level. And so in this way right here, it clearly shows that the sample is an unlikely sample, because there are so many samples we can find, and each sample is supposedly found quite easily. But how can something that's supposedly found quite easily be immediately unlikely upon accepting h of 0, the null hypothesis? And so in that way, in that logic I just now made, then it leads to a further decision that the sample itself is or showing strong evidence. And so now strong evidence for saying that not all population proportions are correct, and saying that not all population proportions claimed are correct, meaning we're supporting H1. And on the other hand, it also means that we are rejecting H of 0. And so there are two ways of saying the sample itself now is proven to be strong evidence for us to, on one hand, to reject the claim in the null hypothesis. The null hypothesis claimed that all population proportions are correct. But now our sample is strong evidence to reject that acceptance. Or we can say that we have strong evidence to support H1. And so in this way, one more time looking at the wording of the question, it is primarily a yes or no question. Is a sample showing strong evidence such and such? And so we apparently had strong evidence. We just now showed that we had strong evidence. So the ultimate answer to the question we're looking at is yes. And so now, as a generalization of the whole problem about performing a chi-square test to test for goodness of fit, then the problem is as following. Let's say, looking back at this table that we were doing, then starting out with a population that is divided into a few categories of concerns right here. So say, for example, throughout our problem, the population of students who take a math course, a certain math course, was divided into the four concerned categories here, being in business major, being a nursing major, being in an engineering major, and being undecided. And so along with the population being divided into the categories as distributed here, there is a claim, or there was a claim, that the proportions, the population proportions for all of these categories are being distributed as given here. So there will always be a given column on the table we're studying here that lists all of the claimed population proportion values. So this is the column that lists all the population proportion values that are claimed here. And after receiving the claim right here, we can test that claim by selecting a sample, and among the sample itself right here, there would be some observed counts along with each of the categories here that will reflect some truth inside of the sample. And so we use the sample to find out whether it shows evidence, so that we can either say that we must reject this original claim that all of the population proportions are being distributed as given here in this table. Or otherwise, if the sample here is not showing strong evidence, then we will fail to reject the claim about all of these values of the population proportions. And so in that way, how I explain, then a lot of times, as common as how we have seen earlier, the way of the problem, the way how the problem is worded can also be quite commonly worded as following: at a given significance level is the sample, this sample of ours right here. And so is the sample showing strong evidence to reject the claim about the population proportions? So that's another way that's quite commonly seen as a way of how the problem is being worded. But so now, in the end, it's all about, we're testing a claim for all of these population proportion values. And all of these population proportion values indicate a way how these categories are being distributed or being fitted in the population. And as I said earlier, the population is divided, it's split into these categories of concern here. And so in that way, if we reject, if this sample shows strong evidence that we can reject the claim, then that means the population is not well fitted with these claimed population proportion values. Or otherwise, if this sample of ours is not strong evidence that we fail to reject the population proportions being claimed here, then that means there's a likeliness the population is well fitted with these being the population proportion values, because we fail to reject H0. That's the reason why the kind of test we were doing here is being regarded as the test for goodness of fit. How good, how well are these proportions being distributed? How well are these categories being fitted in our population? And now, looking back at what I said earlier in the beginning of our video lesson here about how our null hypothesis, as one statement that claims all of these four population proportion values corresponding to these population categories. And so in that way, it allowed me to make another remark here. So if we're looking back at our question that was stated, we're trying to prove that not all population proportions claimed in the hypothesis, in the null hypothesis, are correct. And so at the end of the test we had strong evidence to say that not all of the population proportions are correct. But keep in mind now that throughout the problem, we were never able to point out which one or which ones among these claimed proportions being the incorrect ones. And that is the same as a generality for any other chi-square test for goodness of fit. we can only say that throughout all of these proportions being claimed in our null hypothesis, not all of them are correct, but we will never be able to point out which one or which ones among these proportions being the incorrect ones. And as a matter of fact, we'll never have to point out the incorrect ones in these problems. And then after successfully identifying our goal as stated in the two hypotheses here, then these are the steps that are necessary to follow through to test our hypothesis to find out either we can reject h sub 0 and support h1, or we will fail to reject h sub 0 and not enough evidence to support h1. And so first step was once again to calculate all of the expected counts, and details as well as explanations were all given back in the general lecture. And then after getting all of the expected counts, we're going to calculate all component values. And then after having all component values, then we will be calculating the value for chi-square by summing up all of our component values. Degrees of freedom will always be the number of categories that we're trying to fit here minus 1. And once we've had our chi-square value, we're going to set up the probability, the final p-value always as a right tail test. And again, once we've had the p-value calculated, then the next step is just as standard as any other testing hypothesis problem, where we would compare our final p-value with the given significance level. And that is the decision line for us to decide whether our sample is an unlikely sample or not. And being an unlikely sample, it leads further to the fact that our sample is showing strong evidence for us to now reject the statement in h sub 0 or support the statement in h1. And ultimately, throughout the example that was offered along with the general lecture, then we drew out a few highlighted formulas. So the expected count for at any ith category, or the expected count for any ith category, can be calculated by just simply the sample size multiplied with the claimed proportion for the ith category, and that is the expected count. And of course, we have been expressing any of those claimed population proportions as a decimal. So any piece of I is in decimal. Then the components, as another highlight on any of the categories, is calculated as the difference between observed counts in the particular category with the expected count, then square the difference and divide it by the expected count of the category. And so that is the component value. And at the final step, chi-square is the sum of all components. And we can always find the degrees of freedom for our problem by the number of categories minus 1. And as I was saying back in the general lecture and explaining the steps, then finding degrees of freedom is a step that can be done independently with any other steps. So I, in my own experience, I have never considered this as a formal step, but rather it's just a one truth about any problem that we're doing.